Alright, so here we go. Double derivatives. Double derivatives allow us a really quick way to do the table. We don't need to do the table if we've got double derivatives. Okay, if we can apply double derivative, life is a lot easier. It also allows us time to find our point of inflection. I'll give you a real world example. Here is my object right now. Is there any acceleration applying on this object?
Yes, it's spinning.
Right now, is there any acceleration? Well, yes, there is actually, but anyway, physics is obviously going well. It's in my hand. There is an acceleration due to gravity, but you can't see it right now. But if I throw this object up, is there an acceleration applying on that object?
Yes.
It's a constant negative 9.8, correct? Negative implying down. When I throw it, it's got an upward velocity, so a positive velocity. Just go around the back, thank you. So when I throw it up, there is a positive velocity having a negative acceleration being applied, correct? What am I talking about when I talk about where this is? What's that concept called? The location, what do we call that? Displacement. How do I get velocity from displacement? How do I get acceleration from velocity? Derive it. So what have I done to go from acceleration to, from displacement to acceleration? I have derived it. Now what is, if this was a positive acceleration, what would happen? Keep going forever, correct? Be an interesting cleaning experience for the cleaners, but with a negative double derivative, what happens?
Turns up and down.
Comes back down. What do we call that place when it's at the top?
Peak.
A maximum, correct? Stationary point. So, when we get a negative double derivative, I've done this wrong around. When we get a negative double derivative, gotcha. That'll teach the other finishes. I think concave down, that's a frown. Concave up, that's a cup. Yep, so we get a negative double derivative, we have a maximum, it is concave down. Does that make sense?
What's concave? What's that again?
Concave down means that the accelerator, it's a maximum because the velocity is becoming more negative. Does that make sense? The velocity is becoming more negative, or in this situation, which means that it's only going to go down. Cool? It's concave down. If it's got a positive double derivative, it's concave up. I like to remember concave up like a cup, concave down like a frown. If there is a point, and in this example there is no points of inflection. Why is there no points of inflection in this example? Because our double derivative will never equal zero. What will our double derivative always equal? Negative 9.8, because it never changes, gravity is always there, correct? There are examples like this where that's not always the case. This is a maximum there, correct? So around this point here, what would we expect the double derivative to be?
Zero.
The derivative would be zero at that point. What would the double derivative around that point be? Well, it's a negative, that's all I want. It's negative, I don't care about the value, I just care that it's negative. The double derivative is changing the whole way through there. Cool? But it's negative at that point in time, which means it's concave down, which means it's a maximum, correct? At this point here, it's positive, correct? Where do we reckon our point of inflection is going to occur?
Where it was the x-action.
The point of inflection is where your double derivative is equal to zero. Where do we think it's negative here, and it's positive there? Where do we reckon it's going to occur?
Is that line form?
Halfway between, correct?
Bingo.
Line of equilibrium.
Sorry.
So the point of inflection is where our velocity goes from being negative to, or the change in velocity goes from being negative to positive. Cool? Does that make sense?
Yeah.
You'll also note the point of inflections occur on those sort of graphs there. Cool? So at this point here, our double derivative is zero. Why do you reckon our double derivative is zero there?
Because it changes.
Changes, but is that a max or a min? Neither. Cool? Awesome. So a double derivative allows us to do two things very easily. As long as you get that out of it, you are fine. A point of inflection and tells us about concavity. Yeah, this one will be exactly in the middle. Yeah. Awesome. It won't always be, so if I've got, it won't, no way of saying that that's in there, but because it's a trig function, it will be exactly in the middle. Yeah, okay. So we're going to look at the example we just did very, very quickly, and we're going to look at two questions. Same two questions, or same question to start with. Determine the stationary point, its nature.
That's the layer.
Using double derivatives. The function, for those of us who can't recall, is x cubed plus 2x squared plus x. Cool. We've already derived it, so I don't need to do that again. Well, I do need to do it again, but we don't need to harp on the fact. 3x squared plus 4x plus 1. Cool.
Then do it again.
And then I double derive it. I've already found out my stationary points. So when I double derive that, I get 6x plus 4. Now, if this technique works, we should see a positive value at which? At the minimum.
Yes.
Positive value at the minimum.
Yes.
Concave up. We want the cup. Concave up like the cup. So if this works, when I sub in f double dash, which one's my min?
Negative 1.
I should get a value that's positive, correct? 6 times negative 1 on 3 plus 4. What's negative 1 on 3 times 6? Do I care that it's 2? All I care is that it's positive.
Is this in separate?
Yep. F double dash, what's the other value? And if it works, that should be what? Therefore, it's a maximum. Cool?
So we still have to work out the minimum and maximum before we do that.
Sometimes it'll just ask for a stationary point. Like you won't have to use the table. Sometimes it'll say, what's the nature of the stationary point?
Yeah, so you just have to do the stationary points and everything.
Yeah. We don't always have to sketch them. So in this context, we're sketching all the time, but you wouldn't always have to find the coordinates.
So to use that, we have to follow the stationary points first.
Yeah. So you always, to use this technique, you'll need to find the stationary points and then sub them in. Now, the last question I could possibly ask is, determine
I don't know the way yet.
the point of inflection. So can we please do that now? Determine the point of inflection for that function.
So you just make it
Well, I've got, what happens at every point of inflection in the history of point of inflections? Double derivative equals 0.